Good morning, everyone, or good afternoon, depending on where you're calling from. Welcome to our webinar on air pollution, electric vehicles, and health. My name is Alan McKee. I'm the communications specialist for CANUE, which is the Canadian Urban Environmental Health Research Consortium. I'd like to begin by acknowledging the land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Before we get started, I would like to remind you to please turn your cameras off and stay on mute during the presentation portion of the webinar. If you have questions for our speaker, please put them in the chat and we will have time to answer them at the end. Now it is my pleasure to introduce Dr. Laura Minet. Laura is an assistant professor at the University of Victoria, where she leads the Clean Air Lab, and I'll put more information about their work in the chat. She holds a PhD in civil engineering from the University of Toronto, where she was also a postdoctoral research fellow in the Department of Earth Sciences and Professor Miriam Diamond's Environmental Research Group. Her areas of expertise include air quality, population exposure to air pollution, population health, transportation engineering, vehicle emissions, and dispersion modeling. So we're very pleased to have Laura with us today. Thank you all for coming and joining us, and thank you, Laura, for sparing some time to speak with us today, and I'll turn it over to you.
Thank you, Ellen, for the introduction. Hello, everyone, and thank you so much for hosting me here today. So in today's seminar, I'm going to talk about how electric vehicles have the potential to influence air pollution and health. So vehicle electrification is widely promoted as an opportunity to decrease our greenhouse gas emissions in a context of climate change, but less mentioned, but with significant potential health benefits, are the potential air quality improvements that are associated with a decrease in exhaust emissions from on-road vehicles. A deployment of electric vehicles is associated with an increase in electricity demand and production, however. And so depending on the energy mix, how the electricity is produced, and the location of potentially polluting power plants might observe mixed impact. And so that's why it's important to conduct studies to look at what the impact of electric vehicles would be on air quality and population exposure to air pollution. So this is a brief outline of the different parts of my webinar today. So I'll start discussing the health effects of traffic-related air pollution, also called TRAP. I'll discuss the health and environmental benefits of upgrading and electrifying transportation systems. And finally, I'll finish on discussing the barriers and opportunities to increasing rates of electrifications. So I'll start with the health effects of traffic-related air pollution. So before talking about the health effects of TRAP, I think it's important to remind everyone of what TRAP is, traffic air pollution is. So Health Canada describes TRAP as a mixture of vehicle exhaust, air pollutants formed in the atmosphere, and non-exhaust emissions as TRAP. And so TRAP includes the following air pollutants: particulate matter, PM10 and PM2.5, which are particulates with a diameter lower than 10 and 2.5 microns, as well as ultrafine particles, which have a diameter lower than 0.1 micron. Black carbon is also a TRAP. It's the carbonaceous component of PM. It's also referred to as soot, more or less. We have nitrogen oxides, also called NOx, which are mainly composed of nitrogen oxide and nitrogen dioxide, NO and NO2. We have carbon monoxide, CO, and volatile organic compounds, VOCs, which are compounds that have a high vapor pressure and low water solubilities. Some VOCs are inert. That's the case for methane, for instance, but we also have reactive compounds. And I've also added to the list ground level ozone, which is not directly emitted by vehicles, but it's produced by the reaction of NOx and VOCs. PM2.5, PM10, NOx, CO, and ozone are considered what we call criteria air contaminants CACs, which means that they're health-based criteria that were used to establish the ambient air quality standards for these different pollutants. So now, what are the health effects of those traffic-related air pollutants? So we'll start with PM. So here, this image shows you how deep in your body particulate matter of different sizes can go. So typically, particles with a diameter higher than 5 to 10 microns are going to be screened out by nose hairs. Particulates with the diameter lower than 2.5 microns, so PM 2.5, can bypass the upper respiratory tract and enter your alveoli. Then we have PM1 and PM.1. So these are fine and ultrafine particles. And there are many recent studies that have found that they tend to be more dangerous at the larger particles because of their ability to penetrate more effectively into the respiratory system and to transmit their chemical doses to the lungs and then to the blood. So some health effects of inhalation of particulate matter include premature death in people with heart or lung disease, heart attacks, aggravated asthma, and increased respiratory issues such as coughing and difficulty breathing. So currently, PM 2.5 and PM10 concentrations are regulated in Canada, which means there are ambient concentration standards for those pollutants, but there's no standards for fine and ultrafine particles. The second traffic-related air pollutant we're going to talk about are nitrogen oxides. So NOx are formed whenever any fuel is burned in the air. So at high temperature, you're going to have N2 and O2 that are going to react together and combine to form NO and NO2 to form NOx. The NOx production used to be equally distributed between stationary sources and mobile sources, but now mobile sources are the main contributors, especially in urban areas. The effects on people of exposure to NOx include nose and eye irritation, bronchitis, and pneumonia. And NOx are often used by epidemiologists as what we call a marker of traffic pollution, because in urban areas, high concentrations of NOx are related to high traffic. And so NOx concentration are the highest where there's traffic. The next trap we're talking about is carbon monoxide, CO, which is a colorless, odorless, and tasteless gas. It's caused by the incomplete combustion of any fuel that contains carbon, and it's in the outdoor environment. Its major source is the transportation sector. So CO reacts with the hemoglobin in your blood to create a complex that we call carboxyhemoglobin, so HbCO. And this complex is going to prevent oxygen transfer between the blood and your cells. And that's a process that's reversible. And once CO is removed from the air, the HbCO concentration is going to decrease. HbCO is going to slowly break down. So depending on the concentration, the health effects of exposure to CO can range between shortness of breath, headache, dizziness, and unconsciousness. Smokers have a higher concentration of HbCO than non-smokers, which explains why they typically have a shortness of breath whenever they do a little bit of exercise. And finally, we have ground level ozone, which is what we call a secondary air pollutant. It means that it's formed from the reaction of other pollutants. And in the case of ozone, it's formed from the reaction of nitrogen oxide and VOC. It's called a photochemical oxidant because it requires UV energy from the sun to be formed. So we typically have ozone formation during daylight hours and destruction of ozone during the night. And ozone concentrations are higher on hot and sunny days. Exposure to ozone can cause coughing, asthma, bronchitis, a sore throat, and so on. So to conclude on the health effects of traffic-related air pollutant, it's definitely a serious threat for human health. The health risks associated with air pollution include acute effects, short-term effects associated with exposure to TRAP. That would be stroke, hypertension, and then the longer term, so for exposure over multiple years and decades to those air pollutants, you might see appearance of cancer, diabetes, or asthma. In Canada, there are 15,300 premature deaths yearly that are attributed to exposure to outdoor air pollution. And that corresponds to about $140 billion of health expenses. So now that we all have a good understanding of what traffic-related air pollution is and what its health effects are, I'm going to move on to the core of my presentation, which is assessing the health and environmental benefits of upgrading and electrifying transportation. So I'm going to talk here about research that I have led in the context of the Greater Toronto and Hamilton area, which is also called the GTHA. So I'll more specifically discuss two study cases. So the first study aimed at quantifying the burden of en route vehicles on air quality and on population exposure and health. And the second study looks at more specifically at the climate and health benefits of getting electric vehicles on the roads of the GTHA. So this is the GTHA, the Greater Toronto and Hamilton area. It houses about 7 million inhabitants, and it's divided into 6 regional municipalities: Toronto, Durham, York, Peel, Halton, and Hamilton. Here on this map, the more purplish color is going to highlight population centers. So you see a lot more population in Toronto, Peel, and York regions than in the other regions. So I'll start with presenting a bit the methodological framework that was used to answer the study question that we identified before. So how can we quantify the health burden of vehicles, and how can we quantify the benefits of electrifying vehicles? So to do this, we need to work with what we call a chemical transport model, which is a complex model that simulates the dispersion of air pollutants, but also their chemical reactions. So it's a comprehensive and complex model, which requires information on all types of air pollutant emissions, whether they are natural or anthropogenic emissions, to be able to model the complex chemical reactions that occur between the pollutants in the air. And then it also requires information on land use and meteorology to model how pollutants disperse and how they react between each other. And the output from a chemical transport model are air pollutant concentrations at a fine spatial resolution. So in the case of the study, over the GTHA, the spatial resolution chosen was 1 by 1 kilometers. So the GTHA was basically divided into grid cells in a grid of 1 by 1 kilometer cells. And for each cell, we modeled a specific concentration. So the emission inventory is important for this type of model, and so we need to have the most refined inventory possible. So in this framework, we took into account all sources of air pollutant emissions. So anthropogenic sources such as power plant emissions, traffic emissions, and also industries, agriculture and shipping emissions. And we also took into account natural emissions such as the vegetation, because plants are going to emit a large amount of organic species, such as water organic compounds, VOCs, and those are going to play an important role in the formation of new pollutants. Since traffic is a larger source of emissions in cities, but also because it's the focus of this study, looking at traffic-related air pollutants, we worked on having a traffic emission inventory as detailed as possible. So here we use the results of a traffic assignment model that was based on travel survey data. And so this traffic assignment model provided information on traffic volume and traffic speed along the different roads of the GTHA. And when combined with emission factors, we got an emission inventory for private household vehicles, transit buses, and commercial vehicles. And so here, I'm showing 2 maps of the traffic emissions for PM2.5 and black carbon in the GTHA, and that were obtained from this methodology. So we really see that the highways in the region are standing out. So the more green and more red colors. And we also see higher emission generally in Toronto and Peel regions. But as we move out towards the outside of the GTHA, which are more rural areas, we see that the emissions are lower because there's a lot less traffic. And so finally, to evaluate the impact of changes in air pollutant concentrations on human health, we've assessed the health outcomes associated with changes in air quality. And so those were assessed in terms of changes in years of life lost and number of premature deaths. So changes in air pollutant concentrations that were as output of the chemical transport model could arise, for instance, in our case, from changes in the traffic emissions. So if we change traffic emissions to reflect some electrification scenarios, we obtain different air pollutant concentrations at the end of the chemical transport model. And so comparing the changes in air pollutant concentrations, we could associate them with changes in health outcomes. So how did we quantify years of life lost and number of premature deaths? We use what we call concentration response functions, which relate a change in air pollutant exposure with a change in risk of mortality. So here, if we take the example, the first row for PM 2.5, we have an RR, or risk ratio of 1.1 for and so this risk ratio means that for each increase in exposure by 10 micrograms per cubic meter, there is a 10% increased chance of mortality. So now that I provided an overview of the methodological framework, I'll first give you an idea of which types of vehicles are responsible for the more emissions, at least in the GTHA. So this is an emission inventory for private vehicles, written as trucks here, private vehicles, so cars and SUVs, and public transit buses. So that's that diagram here shows the distribution of traffic-related nitrogen oxide emissions, so NOx emissions. And we see that trucks are responsible for more than half of the traffic-related NOx emissions in the GTHAs, and cars and SUVs are also responsible for a large portion, although lower. This diagram here shows the distribution for black carbon, which is very similar to the distribution for PM 2.5. And here, trucks, again, are the largest emitters of black carbon. More than 70% of traffic-related black carbon emissions in the GTHA are due to trucks. And finally here, I'm showing the same, but this time for greenhouse gas emissions that are expressed in CO2 equivalent. Here, it's not trucks that are responsible for the highest proportion of GHG emission, but it's really cars and SUVs. We also see, so the public transit buses that are in green here, they represent a small portion of the total traffic emissions, but they're important, especially when we talk about NOx and PM 2.5 and black carbon, because they operate in densely populated areas. So their exhaust emissions are going to affect a lot of persons. When we talk about electric vehicles, the initial goal is usually to decrease greenhouse gas emissions. And so when we look at this, it makes sense to be targeting private vehicles because that's where we're going to see the biggest benefits. And so that's why electrification is starting with cars and SUVs. So looking at the first case studies, where we looked at the traffic-related air pollution resulting from different vehicle categories and their health burdens on population of the GTHA. So here, design different study cases. First, we had a base case where we included the emissions of all three vehicle categories, so the private cars and SUVs, the trucks, and then transit buses. And then to evaluate the impact of each one of those vehicle category on air quality in the region, we run study cases where we remove the emissions of each one of those vehicle categories. So we had a study case where we didn't have any emissions from private passenger vehicles, so no cars and SUVs, and the same for commercial vehicles and transit buses. And so the air quality model, the framework I showed you before, was run or the base case, but and each one of those study cases. And the output concentrations from each study case was compared with the base case to look at the differences in concentrations. And those differences in concentrations were later translated into changes or into health outcomes. So here these maps are showing the years of life lost per 100,000 inhabitants that are attributed to each vehicle category. So the red color shows the location with the highest number of years of life lost per capita. So the population losing the most years of life due to private passenger vehicles and commercial vehicles is located mainly along the highways and around the airport, which is in Peel region. Also, the region of Peel is known to have substantial truck traffic, and that's we see that's where we have a lot of red color showing that trucks are responsible for a large number of years of life lost there. The spatial distribution for transit buses is a bit different because they mainly drive in the city of Toronto, and so the population the most affected by emissions from transit buses is located in Toronto. And here I'm also indicating the total number of premature deaths that are induced by the exhaust emissions of each vehicle category. So here we see that all vehicles are responsible for a large number of premature deaths every year, but that's really trucks that are inducing the highest number. So that leads us to the second study case, which really focuses on the electrification of vehicles. So to study the impact of having electric vehicle fleets on population exposure and health, first considers the same base case with private cars and SUVs, public transit buses, and commercial vehicles, so trucks. And then we considered two scenarios. A first scenario where cars and SUVs were 100% electric, and a second scenario where all transit buses were electric. In those two scenarios, the exhaust emissions from the electric vehicles were removed. So there were no exhaust emissions associated with cars and SUVs under scenario one, and there were no exhaust emissions from transit buses in scenario two. But what we added is the emissions associated with the production of electricity needed to fuel those cars and SUVs and transit buses. And here we used the current electricity grid mix of Ontario, which is 9%, about 9% natural gas power plants, and the rest is basically hydro and nuclear power plants. So natural gas power plants are responsible for emissions of air pollutants, but nuclear and hydro is not. And here you notice that there's no scenario on electric trucks. That's because we considered here that electric trucks are not yet a viable solution on a large scale because of issues related to having huge batteries on such vehicles in point. So here, this graph shows the reductions in traffic-related greenhouse gas emissions that are achieved under each of those scenarios. So we see that deploying electric cars and SUVs, which is the scenario in the middle, so the bar in the middle, is what's going to lead to the greatest reductions compared to the base case on the left. And that's the case even when we consider the greenhouse gas emissions associated with the production of electricity. And so this, which is here indicated in green. So even if we have like 9 to 10% of natural gas power plants in Ontario that are emitting greenhouse gases to produce electricity, we still have a significant decrease in GHG emissions when we have 100% of cars and SUVs that are electric. So now looking at the impact on air quality and population health. So those two maps have the same color scheme. And so the greener the color, the more years of life are saved. So this map here shows the years of life saved per 100,000 capita under each of those two scenarios, 100% electric cars and SUVs on the left and 100% of electric transit buses on the right. So we see that both the impacts in terms of health benefits expressed in terms of number of premature death as well, and in terms of GHG emissions. It's really the region of Toronto that's always benefiting the most from the strategies implemented, so electrification of the fleet of vehicle. Tackling emissions from cars would lead to the biggest improvements in air quality and the biggest decreases in greenhouse gas emissions, but it's also important, again, to consider transit buses because they drive in highly populated zones, so they have a lot of impact on, especially here in the population of Toronto. We've also here modeled two scenarios of partial electrification of the cars and SUVs. So on the left is 20% electric vehicle, so electric cars and SUVs. In the middle, it's 50%, and on the right, 100%. So on the right is the same graph at the previous, same map as the previous slide. So with low levels of electrification of the private vehicles, so 20% or 50%, it's mainly the regions of Toronto and Peel that benefit from the improvement of air quality. But what's important to notice here is that the GHG emission savings, as well as the number of premature deaths prevented under those scenarios, are quite proportional to the level of electrification. And so even small penetrations of electric vehicles is going to have an impact on population. So now that we've seen that even in the province, where a part of the electricity is produced by gas power plants that have GHG and air pollutant emissions, even in a province such as Ontario, we see improvements in air quality associated with increased electrification of the vehicles. And so we can understand the clear benefits of electrification and ambient air quality and population health. But I'd like to talk about the barriers and opportunities to increasing the rates of electrification. So what are the strategies to deploy electric vehicles? How can we get more clean vehicles on the road? So first, I believe that focusing on zero emission vehicles or ZEV mandates and purchase incentive is what's going to force automakers to sell a certain percentage of zero emission vehicles, and will give financial support for people to buy an electric vehicle. And so really focusing on this, on national ZEV mandates is what's going to, it's one strategy to deploy electric vehicles. So in this area, the 2030 emission reduction plan from the government of Canada, which was released in 2022, built on the previous mandate targets for 100% light-duty vehicles ZEV sales in 2035 by adding some milestones. So up until this year, the government of Canada was saying, oh, we have this target of achieving 100% zero electric vehicle sales for light-duty vehicles in 2035, but they didn't really have a path to go there. Now we know that the first target is having more than 20% of their sales in 2026 and more than 60% of their sales in 2030. So that's for Canada in general, but some provinces have more ambitious mandates. So for instance, British Columbia was the first jurisdiction in Canada to set a ZEV mandate. So in the 2021 Clean BC Roadmap to 2030, the province set a mandate of 100% electric vehicles by 2035, so the same as Canada. But they have more stringent milestones with more than 26% of ZEV sales in 2026 and more than 90% of ZEV sales in 2030. Quebec as well, the province of Quebec, had put in place ZEV standards in 2018. So automakers that are selling more than 4,500 new vehicles per year must accumulate credits by selling zero emission vehicles on the Quebec market to meet the target, and otherwise they get fined. So they have to sell at least 9.5% of zero emission vehicles to avoid being fined. But what's important to realize is that these mandates for selling new cars are for selling new cars, and they're not for all vehicles, meaning that there's going to be a delay between when we achieve 100% ZEV sales and when we're going to only see electric zero emission vehicles on the roads. So in Canada, light duty vehicles have 12 to 13 years of life. So there might still be some vehicles, gas-powered vehicles sold in 2034, for instance, and it's going to take 12, 13 years to see those vehicles disappear from our roads. And so we would, with this ZEV sales mandate, we would still see gasoline and diesel vehicles on the roads until maybe 2050, the year 2050. Another way to encourage people to acquire electric vehicles would be to maintain their electric vehicle purchase incentives. So acquiring an electric vehicle today necessitates higher upfront expenses than purchasing a conventional vehicle. And so it's essential to provide financial help to support people buying more electric vehicles. So Canada just extended its purchase incentive program for the next 3 years. So anyone purchasing a new battery electric vehicle or plug-in hybrid vehicle or hydrogen fuel cell vehicle could receive up to $5,000 of rebates. On top of that, you have additional rebates by provinces. So British Columbia provides additional incentives of up to $4,000 if you buy a new zero emission vehicle, and that's based on your income. And when you buy a used electric vehicle, there's no provincial sales taxes. Quebec is going to offer an additional extra $7,000 rebate, and this one is not based on the income. Nova Scotia is also providing incentives for new and used vehicles. Those provinces, New Brunswick, PEI, Yukon, they're also providing the highest incentives after Quebec, so up to $5,000. But unfortunately, there are still other provinces that are not providing any other provinces and territories that are not providing any additional incentives. So that would be Ontario, Alberta, Nunavut, and the Northwest territories. Another strategy to deploy more electric vehicles would be to invest in charging stations. That's important to reduce what we call the range anxiety from drivers, which refers to their worry to be stranded without power. So that would include charging at home, whether it's a single detached home or a multi-family building, or charging in public spaces. Provinces are providing level 2 charger rebates in both single detached homes and multifamily residential buildings, and as well as work. So level 2 chargers are so there are 3 levels of charging. Level 1 means plugging into a normal wall outlet. So that might take like 24 hours to charge your electric vehicles, depending on the size of your battery. There's level 3, which is the supercharger. So usually on the highway, when you go for a long trip, you're going to charge your vehicle up to 80% within like half an hour. And so level 2 is in between. So it's going to take the night, basically, to charge your vehicle. And so different provinces are providing some incentives. In British Columbia, you have rebates of up to like $350 for a single detached home, for instance. And there are also more and more regulations for new building constructions across the country where you need to have chargers to be made available to the residents. Canada is also committing to invest $500 million in large-scale ZEVs charging and refueling, but it's hard to know if this is going to be sufficient. And finally, if we strengthen the light-duty GHG emission standards, we will encourage producers to produce and sell more zero-emission vehicles to improve average fleet emissions. So currently in Canada, the emission standards for model year 2017 to 2025 require improvements in the CO2 equivalent emission by about 5% per year. So these regulations require importers and manufacturers of new vehicles to meet fleet average greenhouse gas emission standards. But the use of the term fleet average standard has importance because it means that manufacturers can balance out their fuel economies across different vehicles. So that's here a table from ICCT, that's from 2017, and it shows the different ways standards work across different countries. So in Canada, and this is the last row, we see that manufacturers can average their emission standards across passenger cars and light trucks and over multiple years. So what does it mean? It means that manufacturers have a way to, in practice, increase the GHG emissions of some of their vehicles if they balance them out with other vehicles. And so that's especially convenient if they sell electric vehicles, because they're going to reduce the fleet average GHG emission by selling more electric vehicles. But there could be non-electric vehicles, so conventional vehicles that are actually emitting a lot more than they currently do. So having a more stringent system of regulating GHG efficiency standards would better support the deployment of electric vehicles, but also better support vehicles that have lower GHG emissions. And finally, for electric buses, but I won't go too much into detail on those, but we need a commitment from transit authorities to purchase exclusively electric buses and retire their diesel buses. So some transit authorities in the GTHA, in Quebec, other locations have already committed to buying only electric buses, but more should be concerned. And this would require a bit more funding, probably support from federal and provincial governments because of the high cost of electric buses, especially since the pandemic happened, where the revenues from public transit agencies have substantially decreased. To conclude, I also wanted to mention the issues that are related to a massive electrification of the vehicle fleet. Technically, Canada has the capacity to accommodate close to 100% electric vehicles in terms of electricity production and electricity infrastructure, but we need to manage the load of electricity, and that's more challenging. So when are people going to charge their vehicles? Will this align with the peak demand? How do we plan to store electricity so that it could be available when needed? But a massive electrification is also put a strain on critical material supply chains, especially on those following: lithium, cobalt, manganese, and nickel. So cobalt is one of the most critical because a large portion of it is produced in the Congo Republic. And so lots of battery manufacturers, such as Tesla, are moving away from cobalt-based batteries. Lithium is also widely used in batteries, and so the challenge is more in the amount we need to produce to be able to lead to a massive electrification of the fleets. So just to conclude, electric vehicles are a path toward reducing our GHG emissions and improving our ambient air quality in urban areas and improving population health. But this is not going to solve all of our issues because it might create some constraints on other systems, such as critical materials. And so reducing our dependency on private vehicles remains the best approach to improving ambient air quality. So before moving on to the question, I'd like to acknowledge that the project I presented here have been possible thanks to meaningful collaborations while I was doing my PhD at the University of Toronto, and I'm very grateful for this. And so this concludes my presentation, and I'll be happy to take any questions.